Welcome back to Whispering Universes, where we explore the grandest visions of cosmic engineering and the quiet mysteries that await us among the stars. Tonight, we turn our gaze toward an idea so audacious, so transformative, that it challenges everything we thought possible about the future of intelligent life in the cosmos. Imagine standing at the edge of your solar system, looking back not at a single bright star, but at a vast shell of habitats and collectors, a gossamer sphere of engineering that captures nearly every photon your sun produces. Imagine harnessing not a fraction of your star's power, but all of it, redirecting that ancient fire toward purposes we can barely conceive. This is the dream of stellar engineering, a vision where civilizations don't merely inhabit planets, but rebuild entire solar systems to suit their needs. Where the very architecture of space becomes a canvas for transformation. Where humanity, or beings like us scattered across the galaxy, might one day wrap their parent stars in structures of such magnificence that they would be visible across interstellar distances. Beacons announcing the presence of technological life. The concept emerged from the mind of Freeman Dyson, a British-American physicist whose imagination ranged freely across the boundaries of what seemed possible. In the spring of 1960, Dyson published a paper that would forever change how we think about advanced civilizations. He asked a simple question: what would a truly mature technological society do with its energy resources? His answer was revolutionary. Rather than remaining confined to a single world, forever limited by the trickle of sunlight that happened to fall on their planet's surface, they would expand outward, building structures to capture more and more of their star's output, eventually surrounding it completely. Dyson wasn't proposing a solid shell like something from science fiction. Instead, he imagined a swarm of independent habitats and collectors, each in its own orbit, together forming a cloud that would intercept the majority of the star's radiation. The waste heat from all this collected energy would glow in the infrared, creating a distinctive signature that could be detected by astronomers searching for technological civilizations. We might not see these civilizations in visible light, their stars dimmed or hidden by their engineering, but we would see them in the warmth they radiated, the inevitable byproduct of using energy on such cosmic scales. This vision touches something deep in the human spirit. Throughout our history, we have been builders. We have transformed our environment, reshaped landscapes, constructed cities that glow like constellations when seen from space. The story of human progress has been, in many ways, a story of increasing energy use. From the first fires that pushed back the darkness, to the Industrial Revolution that harnessed steam and electricity, to the nuclear age that learned to tap the binding energy of atoms themselves, each threshold has opened new possibilities for civilization. Stellar engineering is simply the next step in this progression, carried to its logical conclusion. If we continue to grow, continue to expand our capabilities and our reach, eventually we must look beyond our planet, beyond even our planetary neighborhood, toward the greatest power source available to us, the star at the center of our solar system. The sun pours 400 trillion watts into the void every second. Earth intercepts less than a billionth of this output. The rest radiates away into empty space, energy that could, in principle, support billions of times our current civilization. But Dyson spheres are more than just power collectors. They represent a fundamental shift in how we understand our place in the cosmos. For most of human history, we have been passengers, riding on a world we didn't choose, warmed by a star we couldn't control, subject to forces vastly beyond our influence. Stellar engineering suggests a future where we become authors of our own cosmic environment, where we take responsibility not just for our planet, but for our entire solar system, where we transform from observers of nature to participants in shaping the very structure of space around us. The implications ripple outward in every direction. If such structures are possible, if civilizations actually build them, then the universe should be filled with their signatures. Astronomers have spent decades searching for these signs, looking for stars that shine too dimly in visible light but glow brightly in infrared, stars that exhibit the patterns we would expect from partial or complete Dyson structures. So far, we found intriguing candidates, anomalies that don't fit standard models, but nothing conclusive. The search continues, a modern quest that combines cutting-edge astronomy with the ancient human desire to know, are we alone? Here on Whispering Universes, we'll explore every aspect of this magnificent vision. We'll delve into the physics that makes stellar engineering possible, the engineering challenges that must be overcome, the various designs that have been proposed over the decades since Dyson's original paper. We'll examine the astronomical searches underway, the detective work involved in distinguishing natural phenomena from possible signs of technology. And we'll contemplate what it might mean for humanity to undertake such a project, the philosophical and practical transformations that would be required. This is not science fiction, though it has inspired countless stories. This is serious physics and engineering, discussed in peer-reviewed papers, debated at conferences, incorporated into the formal search for extraterrestrial intelligence. It represents our best guess at what truly advanced civilizations might achieve, and what we ourselves might become, given enough time and wisdom. So settle in, let your mind expand to encompass these vast scales, and join us as we explore the grandest construction projects ever imagined. Structures that could wrap stars, harness the total energy output of suns, and announce the presence of technological life to anyone watching from across the galaxy. Welcome to the age of stellar engineering, where dreams are measured in astronomical units, and the future glows warm against the cosmic dark. Freeman Dyson was born in Crowthorne, England, in 1923, a child of the early 20th century who would live to see humanity split the atom, reach the moon, and peer back to the very edge of the observable universe. His mind ranged across physics with uncommon freedom, contributing to quantum electrodynamics, nuclear engineering, and speculative cosmology. But perhaps his most enduring legacy came from a brief paper published in the journal Science in 1960, titled Search for Artificial Stellar Sources of Infrared Radiation. The paper was only 2 pages long, yet it contained an idea that would reverberate through decades of scientific thought. Dyson began with a simple observation. Any technological civilization that continued to grow would eventually face energy constraints. On Earth, our energy consumption had been doubling roughly every few decades throughout the industrial age. Even if this growth slowed, even if it leveled off at some sustainable rate, the fundamental physics suggested that advanced civilizations would seek to maximize their available energy resources. The most abundant source of energy in any solar system is the central star. Our Sun, for instance, converts 4 million tons of matter into pure energy every second through nuclear fusion in its core. This energy streams outward as electromagnetic radiation, most of it in the form of visible light and infrared heat. A mature civilization, Dyson reasoned, would not be content to capture only the tiny fraction that happens to fall on their home planet. They would build structures to intercept more and more of this output. Dyson explicitly rejected the notion of a solid shell surrounding the star, what he called the nightmare of science fiction. Such a structure would be impossibly massive, require materials far stronger than anything known to physics, and face insurmountable engineering challenges regarding stability and temperature control. Instead, he proposed what we now call a Dyson swarm, a vast collection of independent objects, each in its own orbit around the star, together forming a cloud that intercepts a significant fraction of the stellar radiation. These objects might be habitats, rotating structures providing artificial gravity for billions or trillions of inhabitants. They might be industrial facilities, using the collected energy to manufacture ever more components for the growing swarm. They might be solar collectors, vast, thin films designed purely to capture photons and convert them to usable power. The specific designs didn't matter for Dyson's purpose. What mattered was the inevitable consequence. All this collected energy would eventually be radiated away as waste heat, primarily in the infrared portion of the spectrum. This waste heat would create a distinctive signature. A star surrounded by a complete Dyson sphere would be invisible in visible light, all its optical radiation absorbed by the structure. But it would glow brightly in infrared, its temperature determined by the balance between energy absorbed from the star and energy radiated into space. Dyson calculated that for a structure surrounding a sun-like star, this equilibrium temperature would be around 200 to 300 Kelvin, roughly the temperature of Antarctica on Earth. The spectrum would peak in the far infrared at wavelengths of around 10 micrometers. This meant astronomers could search for Dyson spheres, They could look for objects that appeared as infrared sources without corresponding visible light counterparts. Or they could look for stars that seemed dimmer than expected in visible light but brighter than expected in infrared. Even partially completed Dyson swarms would show anomalous infrared excess, detectable with sensitive enough instruments. Dyson's paper was revolutionary because it provided a testable hypothesis about alien civilizations. Rather than engaging in purely philosophical speculation about whether life existed elsewhere in the universe, astronomers could now mount systematic searches using actual telescopes and detectors. They could collect data, analyze spectra, and look for the specific signatures that Dyson's physics predicted. The search for extraterrestrial intelligence became, in part, an observational science. The timing was significant. The 1960s marked the beginning of the space age, a period of unbounded optimism about humanity's future in the cosmos. The first artificial satellites had been launched just a few years earlier. Humans would walk on the moon before the decade was out. Nuclear power promised unlimited clean energy. The idea that we might someday wrap our solar system in a shell of habitats and collectors didn't seem absurd. It seemed like the natural next step in our expansion into space. Dyson himself was careful to note the speculative nature of his proposal. He wasn't predicting that such structures existed or that humanity would definitely build them. He was simply pointing out that if advanced technological civilizations existed and followed certain logical paths of development, they would leave detectable traces. The absence of such traces, if searches came up empty, would itself be interesting information about the prevalence and behavior of intelligent life in the galaxy. The reaction to Dyson's paper was mixed. Some scientists embraced it as a profound insight into the possible manifestations of advanced technology. Others dismissed it as wild speculation, too far removed from testable physics to be worth serious attention. But it sparked conversations, inspired research, and entered the cultural consciousness. The term Dyson Sphere became shorthand for megastructure engineering, appearing in countless science fiction stories, scientific papers, and philosophical discussions about humanity's cosmic future. Looking back across the decades since that 1960 publication, we can see how Dyson's idea has evolved and deepened. Subsequent researchers have explored variations on the basic concept, calculated constraints based on material science and orbital mechanics, and proposed increasingly sophisticated search strategies. The dream of stellar engineering has become firmly embedded in how we think about advanced civilizations, a benchmark against which we measure technological maturity. To understand why Dyson spheres represent such an attractive proposition for advanced civilizations, we must first understand the physics of stars themselves, the nuclear furnaces at their hearts, the tremendous power outputs they sustain for billions of years, and the fundamental laws governing how this energy flows outward into space. At the center of our Sun, deep beneath hundreds of thousands of kilometers of hot plasma, lies a region where temperature and pressure reach extremes that seem almost incomprehensible. The core temperature exceeds 15 million Kelvin. The pressure equals hundreds of billions of Earth atmospheres. Under these conditions, hydrogen nuclei move fast enough and approach close enough to overcome their electrical repulsion and fuse together, forming helium in a process that releases tremendous amounts of energy. This is the proton-proton chain, the primary fusion reaction that powers the Sun and all stars of similar mass. 4 hydrogen nuclei combine through a series of steps to create one helium nucleus, 2 positrons, 2 neutrinos, and most importantly, about 26.7 million electron volts of energy. This may seem like a tiny amount, barely enough to lift a speck of dust, but when multiplied by the countless trillions of reactions occurring every second in the solar core, it adds up to an output of 3.8 times 10 to the 26 watts. To put this in perspective, if we could somehow capture the Sun's total output for just 1 second, it would provide enough energy to meet human civilization's current needs for several 100,000 years. Every second, the Sun converts 4.3 million tons of matter into pure energy, according to Einstein's famous equation, E equals mc squared. This mass loss is negligible compared to the Sun's total mass of 2 times 10 to the 30 kilograms, which is why the Sun can sustain this reaction for billions of years without significant change. The energy released in the core doesn't immediately escape into space. Instead, It begins a slow, tortuous journey outward through the stellar interior. Photons produced by fusion are absorbed and re-emitted countless times by the dense plasma surrounding the core. Each interaction randomizes the photon's direction, so rather than traveling directly outward, the energy takes what physicists call a random walk. A photon that would take just over 2 seconds to travel from the sun's core to its surface in a straight line instead takes something like 100,000 years to make the same journey through the maze of interactions. As the energy works its way outward, the temperature and pressure gradually decrease. In the outer third of the sun's radius, the temperature drops low enough that convection becomes important. Hot plasma rises, cools near the surface, and sinks back down in giant circulation patterns that give the solar surface its granular appearance. Finally, the energy reaches the photosphere, the visible surface of the sun, where it can escape as electromagnetic radiation. The spectrum of this radiation follows the laws of blackbody physics. The sun's surface temperature of about 5,800 Kelvin produces radiation that peaks in the yellow-green portion of the visible spectrum. This is why the sun appears yellowish to our eyes, and why life on Earth evolved to be most sensitive to these wavelengths. But the solar spectrum extends far beyond the visible, from high-energy ultraviolet and X-rays at the short wavelength end to infrared and radio waves at the long wavelength end. This broad spectrum of radiation pours outward in all directions, carrying the energy generated in the solar core out into the solar system and beyond. At Earth's distance from the sun, about 150 million kilometers, the intensity of this radiation equals about 1,360 watts per square meter. This is called the solar constant, though it actually varies slightly with the solar cycle. Over the course of a year, Earth intercepts a total of about 174 petawatts of solar energy, tens of thousands of times more than current human civilization uses. But Earth intercepts only a tiny fraction of the sun's total output. Imagine a sphere surrounding the sun at Earth's orbital distance. The surface area of this sphere would equal 2.8 times 10 to the 23rd square meters. The sun's energy spreads across this entire vast area, which is why the intensity decreases with distance according to the inverse square law. Most of the sun's energy streams past Earth and the other planets, radiating away into interstellar space where it contributes nothing to anyone. This is the fundamental inefficiency that Dyson identified. From an engineering perspective, a star left to itself is a tremendously wasteful power source. More than 99.9999999% of its output serves no purpose for any planetary civilization. This energy could, in principle, support structures and populations beyond anything we can currently imagine. The question becomes not whether advanced civilizations would want to capture this energy, but whether they could develop the technologies to do so. The physics of stellar energy also determines the constraints on any Dyson structure. Whatever design we choose must handle energy flows, measured in yottawatts, temperatures that can vaporize any material if concentrated too densely, and radiation pressures that can push objects away from the star. The structure must maintain stable orbits over timescales of centuries or millennia, resist degradation from the harsh space environment, and convert or use the captured energy efficiently enough that waste heat doesn't cause the structure itself to overheat and fail. These challenges are immense, but they're not obviously impossible. The laws of physics permit such structures. They just require engineering capabilities far beyond our current level. Understanding stellar physics is the first step toward imagining how we might someday harness it. One of the most difficult aspects of stellar engineering to grasp is the sheer scale involved. We're accustomed to thinking in human dimensions, meters and kilometers, kilograms and tons, watts and megawatts. But Dyson structures operate at scales so vast that our everyday intuitions completely fail. Let's explore these scales systematically, building up from the familiar to the cosmic. Consider first the distance from Earth to the Sun, 1 astronomical unit, or about 150 million kilometers. This is the fundamental distance scale in our solar system. Light, traveling at 300,000 kilometers per second, takes 8 minutes and 20 seconds to cover this distance. If you could somehow build a highway to the Sun and drive at freeway speeds, the journey would take about 170 years. A Dyson swarm, built at 1 astronomical unit from the Sun, would need to fill a sphere with a surface area of about 280 trillion square meters. To visualize this, imagine trying to pave this entire sphere with solar panels. If each panel measured 1 meter by 1 meter, you would need 280 trillion panels. If you manufactured 1 million panels per second, working around the clock, it would take you 9 trillion years to complete the job, longer than the current age of the universe. Now consider the mass requirements. Even if we imagine incredibly thin structures, gossamer films, just micrometers thick, the total mass required would be staggering. Let's assume our Dyson swarm consists of structures made primarily of silicon and metals, with an average density similar to solar panels. If we built a complete shell just 1 meter thick at 1 astronomical unit, we would need a mass of about 2.2 times 10 to the 26 kilograms. How much mass is this? The planet Mercury has a mass of 3.3 times 10 to the 23 kilograms. Our hypothetical Dyson shell would require dismantling about 700 planets the size of Mercury. Even if we could somehow build structures just 1 millimeter thick, we'd still need to disassemble several Mercury-sized bodies. And this assumes perfect efficiency, no waste, and materials with exactly the properties we need. Realistic engineering would require even more raw materials to account for support structures, redundancy, and safety margins. The energy scales are equally overwhelming. We mentioned earlier that the sun outputs 3.8 times 10 to the 26 watts. Current human civilization uses about 18 terawatts on average, or 1.8 times 10 to the 13 watts. The sun produces more than 20 trillion times more energy every second than all of human civilization currently uses. If we could capture just 1% of the sun's output, we would have access to 200 trillion times our current energy budget. What could a civilization do with such energy? It's difficult to even imagine. We might power continent-sized data centers, running artificial intelligences of incomprehensible sophistication. We might accelerate spacecraft to relativistic velocities, sending robotic probes or even crewed vessels to nearby star systems. We might engage in transmutation and synthesis, creating exotic materials atom by atom. We might run simulated universes, digital realms as complex as physical reality. We might beam power to distant outposts, supporting human expansion throughout the solar system and beyond. The construction timescales are also worth considering. Let's imagine a more modest scenario, where we want to build a partial Dyson swarm that captures just 1% of the sun's output. We decide to use asteroid material, self-replicating robots that can mine asteroids, refine the materials, and construct new panels and habitats. We start with one factory and program it to build a copy of itself before beginning production of actual Dyson components. If our factories can replicate every year, we'd have 2 factories after year 1, 4 after year 2, 8 after year 3, and so on. After 20 years of exponential growth, we'd have over 1 million factories. After 30 years, over 1 billion. This exponential replication is powerful, but even with billions of factories, each producing huge amounts of material, it would still take centuries to build even a sparse Dyson swarm. Or consider the orbital mechanics. For a Dyson swarm to function, each component must be in a stable orbit around the sunday. Objects at 1 astronomical unit orbit with a period of 1 Earth year, moving at about 30 kilometers per second. We would need to place components in a complex network of orbits, ensuring they don't collide with each other, while collectively intercepting a large fraction of the sun's light. The orbital choreography alone would be an immense computational challenge, requiring constant monitoring and adjustment. The waste heat management presents its own scale challenges. Even if our Dyson structure uses energy with high efficiency, the second law of thermodynamics ensures that some fraction will be degraded to heat. For a complete Dyson sphere, absorbing the sun's full output, this waste heat must be radiated into space from the outer surface. The temperature required to radiate 3.8 times 10 to the 26 watts depends on the surface area and emissivity of the structure. But using Stefan Boltzmann's law, we can calculate that a sphere at 1 astronomical unit would settle at around 300 Kelvin, comfortable for human habitation, but requiring careful thermal engineering. These scales, vast beyond ordinary comprehension, define both the challenge and the promise of stellar engineering. They show us that such projects would require resources and capabilities far exceeding anything humanity has yet achieved. But they also reveal the tremendous payoff: access to energy and resources sufficient to support civilizations billions of times larger and more capable than ours. Thriving in a solar system transformed into a carefully managed environment, all powered by the ancient fires of stellar fusion. In 1964, just 4 years after Dyson published his paper on artificial stellar sources, a Soviet astronomer named Nikolai Kardashev proposed a framework that would become fundamental to how we think about advanced civilizations. He suggested a scale based on energy consumption, a ladder of technological development that could, in principle, extend across cosmic timescales. Kardashev's scale originally had 3 levels, though subsequent researchers have proposed extensions and refinements. A Type I civilization, in Kardashev's conception, would be able to harness all the energy resources of its home planet. For Earth, this means something on the order of 10 to the 16 watts, the total amount of energy Earth receives from the Sun, plus geothermal and tidal energy sources. A Type I civilization would have complete control over planetary weather, could prevent asteroid impacts, and would have colonized most or all of their world. Humanity has not yet reached Type I status. In the 1960s, astronomer Carl Sagan calculated that we were at about Type 0.7, and subsequent estimates place us around Type 0.73 today. We use fossil fuels extracted from beneath the surface, nuclear energy from mined uranium, and a growing fraction of solar, wind, and hydroelectric power. We're approaching planetary scale. In some respects, our activities affect global climate. We've explored most of the planet's surface. We can communicate instantly across continents, but we haven't achieved full mastery of planetary energy resources. A Type II civilization, in Kardashev's scheme, would harness the total energy output of its parent star. This is precisely what Dyson Spheres and similar megastructures would enable. The jump from Type I to Type II represents an increase in energy use of roughly 10 billion times. It's not just a quantitative change, but a qualitative transformation, marking the transition from a planetary civilization to one that has spread throughout an entire solar system, reconfiguring the very structure of space around its star. Such a civilization would be unrecognizable to us in many ways. With access to stellar-scale energy, they could engage in projects that seem like magic from our current perspective. They might terraform planets wholesale, boil away the atmospheres of gas giants to access metallic hydrogen in their cores, or create artificial habitats larger than worlds. They could send interstellar probes in vast numbers, exploring nearby star systems, and perhaps even establishing colonies around other suns. They would be able to survive the death of their home planet, having long since moved most of their population and infrastructure into space-based habitats. A Type III civilization would command the energy resources of an entire galaxy, something like 10 to the 36 watts or more. This is the province of true cosmic engineering. Civilizations that might move stars, harvest supermassive black holes, or create structures visible from across intergalactic distances. Kardashev proposed this level as a theoretical possibility, though the engineering challenges and physical constraints become almost impossible to imagine at this scale. The relevance of Kardashev's scale to stellar engineering is profound. It provides a framework for thinking about the trajectory of technological development over very long timescales. If civilizations continue to grow and progress, if they don't destroy themselves or stagnate at some lower level, then movement up the Kardashev scale becomes a natural consequence. The transition to Type II, requiring the construction of something like a Dyson sphere, becomes not an exotic possibility, but an expected milestone in the maturation of intelligent life. This perspective has implications for how we search for extraterrestrial civilizations. If most advanced civilizations do build Dyson structures as they approach Type II status, then we should be able to detect them through their infrared signatures. The absence of such signatures in our astronomical surveys could indicate that either intelligent life is rare, or civilizations tend to not survive long enough to reach Type II, or they choose not to build these structures for reasons we don't yet understand. Each possibility tells us something important about the universe and our place in it. The timescales involved in climbing the Kardashev ladder are also instructive. If we extrapolate current trends in human energy consumption, Doubling roughly every 20 to 50 years, we might reach Type I status within a few centuries. Continuing at similar rates of growth, we might approach Type II in several thousand years. These are long times by human standards, but mere instants in cosmic history. Our sun will continue burning for another 5 billion years. In principle, there's plenty of time for patient, persistent engineering to transform our solar system. Critics of the Kardashev scale note that it assumes energy consumption continues to grow exponentially, which may not be realistic over very long periods. Civilizations might reach a stable equilibrium where energy use plateaus at a level sufficient for their needs, but far below the theoretical maximum. They might develop technologies that make them more efficient, rather than simply larger. They might choose to limit their growth for philosophical or environmental reasons. These criticisms are valid, and Kardashev himself would likely have acknowledged them. The scale isn't meant as a prediction, but as a conceptual tool, a way to categorize and think about different levels of technological capability. It highlights the tremendous energy resources available to civilizations that expand beyond their home planets, and suggests that the most visible signs of advanced technology in the cosmos might be the megastructures built to capture stellar energy. Freeman Dyson's spheres, then, can be understood as the signature of civilizations transitioning from Type I to Type II on Kardashev's ladder. They represent a specific technological milestone, the point at which a civilization has grown beyond planetary constraints and begun to reshape its solar system to meet its energy needs. Whether humanity will make this transition and what form our particular approach to stellar engineering might take remains to be seen. Building a Dyson sphere is not simply a construction project. It represents a complete transformation of a civilization's industrial capabilities, social organization, and relationship with the physical world. To understand what would be required, let's consider the stages such a project might follow and the profound changes it would entail. The first stage would be developing space-based industry. Currently, humans manufacture essentially everything on Earth's surface, using materials extracted from the Earth's crust, working in Earth's gravity, breathing Earth's atmosphere. Building structures at one astronomical unit from the Sun requires moving manufacturing into space, where materials can be shaped in microgravity, solar power is abundant, and there's no atmosphere to limit the size or form of constructed objects. This transition has already begun in small ways. We've conducted manufacturing experiments on the International Space Station, demonstrating that certain materials can be produced better in microgravity than on Earth. We've discussed mining, asteroids for precious metals and water, but these are tiny first steps compared to what stellar engineering would require. We would need orbital factories capable of processing millions of tons of raw materials per year, refineries that could extract pure elements from asteroid and comet material, assembly facilities that could construct components measuring kilometers across. The asteroids would become our primary source of material. The asteroid belt between Mars and Jupiter contains millions of rocky bodies with a total mass of perhaps 3 × 10 to the 21 kilograms. This sounds like a lot, but recall that a complete Dyson sphere at one astronomical unit might require 2.2 × 10 to the 26 kilograms, about 100,000 times the mass of the entire asteroid belt. We would need to dismantle multiple planets, likely starting with Mercury, which is closest to the Sun and most energy-intensive to reach from Earth, but also closest to where we want to build. Self-replicating machinery would be essential. Humans could not possibly construct a Dyson sphere through manual labor. The scales are too vast and the timescales too long. Instead, we would need to develop robots that could mine asteroids or planetary material, extract the necessary elements, and construct not only Dyson components, but also copies of themselves. These machines would be the true builders of the sphere, spreading exponentially through the solar system like a mechanical forest, each generation constructing the next, while also building the megastructure itself. The mathematics of exponential replication are powerful, but also concerning. A replication time of 1 year, with each factory producing one copy of itself before switching to Dyson component production, would yield over 1 million factories after 20 doubts. But this exponential growth must be carefully controlled. Uncontrolled replication could turn the solar system into grey goo, everything converted to factory mass with nothing left for the actual purpose. Safeguards, limitations, and oversight would be crucial. Energy requirements for the construction phase would be enormous. Mining and refining materials requires energy, as does transporting components, assembling structures, and maintaining orbits. Fortunately, the Sun provides essentially unlimited power, and as each section of the Dyson swarm comes online, it begins contributing to the overall energy budget. The construction would bootstrap itself, early components providing power for later stages, creating a positive feedback loop where the growing structure enables accelerated expansion. The social and economic transformation would be equally profound. Building a Dyson sphere would require long-term planning and coordination across centuries or millennia. No single generation would see the project completed. Political structures would need to be stable enough to maintain this vision across countless human lifetimes. Economic systems would need to support investment in infrastructure that wouldn't yield returns for hundreds of years. Cultural values would need to emphasize the long-term future over immediate gratification. This might seem impossible from our current perspective, where election cycles last a few years and corporate planning rarely extends beyond a decade, but other civilizations have built structures that took generations. Medieval cathedrals sometimes required a century or more to complete, with workers knowing they would never see the finished building. The Great Wall of China grew over centuries through the efforts of countless individuals. Perhaps as humanity matures, as we extend our lifespan through medical advances and our planning through better institutions, we could develop the patience required for truly long-term projects. The transition to space-based habitation would accompany the industrial transformation. As we built our Dyson swarm, we would also be constructing habitats where people could live and work. These wouldn't be mere space stations, but rotating cylinders or spheres, potentially tens of kilometers across, providing Earth-normal gravity through rotation and supporting complete ecosystems. The population living in space would grow as construction progressed, until eventually more humans lived in orbital habitats than on planets. This shift would change fundamental aspects of human identity. Earth would no longer be our only home, but one location among thousands or millions. Human culture would diversify as habitats develop their own local customs and traditions, separated by millions of kilometers and different orbital mechanics. Yet, the shared project of building the Dyson swarm would provide a common purpose, a unifying goal that transcended individual habitat rivalries. Safety and redundancy would be paramount. In space, there's no atmosphere to breathe, no ground to stand on, no emergency services minutes away. Habitat failures could kill thousands. Construction accidents could destroy years of work. We would need to build multiple redundant systems, maintain reserves of critical resources, develop sophisticated repair and response capabilities. The culture of space-based civilization would necessarily be one that took safety seriously, that planned carefully, that tested thoroughly before deployment. All of this, the industrial transformation, the development of self-replicating machines, the creation of space habitats, the social reorganization, would be prerequisites for building a Dyson sphere. They represent challenges as formidable as the construction itself, transformations that would remake human civilization into something adapted for life on the cosmic scale. As we contemplate the distant future of stellar engineering, it's worth considering where humanity stands now and what steps we might plausibly take in the nearer term. We are, after all, barely beginning our journey into space, infants reaching out toward a vast cosmos we've only just started to explore. Our current capabilities in space are impressive by historical standards, but tiny compared to what stellar engineering would require. We've sent humans to the moon and returned them safely, a feat accomplished in the 1960s and 1970s that hasn't been repeated in recent decades. We maintain a permanent presence on the International Space Station, where astronauts conduct research in microgravity. We've sent robotic probes to every planet in the solar system and beyond, our most distant spacecraft now entering interstellar space after decades of travel. These achievements demonstrate that space travel and operation are possible, that humans can work in the harsh environment beyond Earth's atmosphere, that we can build complex systems that function reliably for years or decades. But the gap between an orbital space station hosting a handful of astronauts and a Dyson swarm housing trillions remains almost incomprehensibly vast. The first realistic step towards stellar engineering might be establishing a self-sufficient presence on the moon. The lunar surface offers resources including water ice in permanently shadowed craters, metals in the regolith, and abundant solar energy. A lunar base could learn to manufacture using in-situ resources, develop life support systems that recycle everything, and serve as a proving ground for technologies needed for larger space settlements. Several space agencies and private companies have announced plans for lunar bases in the coming decades, though whether these plans will materialize remains uncertain. Asteroid mining represents another near-term possibility. Some near-Earth asteroids contain metals, including gold, platinum, and rare earth elements that are valuable on Earth. Other asteroids are rich in water ice, which could be split into hydrogen and oxygen for rocket fuel. A successful asteroid mining industry would establish the infrastructure for space-based resource extraction and processing, key capabilities for any larger megastructure project. Several startup companies have been founded with this goal, though none have yet succeeded in mining an asteroid. Space-based solar power could be an intermediate step toward Dyson structures. The concept involves placing large solar arrays in Earth orbit, where they would have constant sunlight without atmospheric interference, and beaming the collected energy back to Earth as microwaves or lasers. This would provide clean, reliable power while also developing technologies for large space structures, orbital construction, and long-distance power transmission. Some feasibility studies have been conducted, and the concept may become economically viable as launch costs decrease. Orbital habitats might emerge from space tourism and research. If launch costs fall enough that significant numbers of people can afford to visit space, we might see the construction of larger facilities to accommodate them: hotels, research stations, manufacturing facilities. These would be tiny compared to the rotating cylinders envisioned for a mature Dyson swarm, but they would establish the basic technologies and social patterns of space-based living. Self-replicating machines remain primarily in the realm of research and speculation. We can build robots that perform complex tasks, and we can program them with instructions, but we don't yet have machines that can independently mine raw materials, refine them, manufacture components, and assemble copies of themselves. This capability would require advances in robotics, artificial intelligence, and automated manufacturing that may still be decades away. Some researchers work on 3D printers that can fabricate copies of themselves, small steps toward true self-replication, but much work remains. Fusion energy, while not strictly necessary for stellar engineering, would provide a powerful tool for space-based industry. If we could master controlled fusion, creating miniature stars in magnetic bottles, we would have portable, high-power energy sources that don't depend on sunlight. Fusion-powered rockets could travel quickly throughout the solar system. Fusion reactors could power asteroid mining operations in the dark outer reaches beyond Mars. And fusion torches could transmute elements for manufacturing. After decades of research, fusion power seems to be approaching practical reality, with several experiments achieving significant milestones in recent years. The timescale for humanity's progress towards stellar engineering is difficult to predict. Optimistic scenarios suggest we might establish lunar bases within a few decades, begin asteroid mining in the second half of this century, and have significant space-based industry by 2100. If progress continues, we might construct the first large orbital habitats in the 22nd century, begin serious planning for a Dyson swarm in the 23rd, and have the first components operational by the 24th. This would place the completion of even a partial Dyson structure several centuries in the future, within the lifespan of a long-lived civilization, but far beyond the horizon of current human planning. More conservative estimates might push these timelines back by centuries or even millennia. Much depends on factors we can't predict, whether humanity can overcome current challenges like climate change and political conflict, whether we can develop the necessary technologies, whether we maintain the will and resources to continue expansion into space, whether we encounter unforeseen obstacles that make stellar engineering impractical or impossible. But the trajectory seems clear. We've begun reaching into space, taking our first tentative steps away from our home planet. The resources are out there, energy streaming from the sun, materials in asteroids and moons, space itself providing room for expansion beyond anything possible on Earth's crowded surface. If we survive and continue to develop, the logic of stellar engineering becomes increasingly compelling. We may not build Freeman Dyson's spheres, but we will likely build something, structures that capture more and more of the sun's energy and support a human presence spread throughout the solar system. These first steps we're taking now, these lunar missions and asteroid surveys and orbital experiments, these are the foundation on which future generations will build. They seem modest, even mundane, compared to visions of spheres wrapping stars, but they're real, achievable, and necessary. The journey to stellar engineering begins with a single launch, and we've already begun. When Freeman Dyson first proposed his concept in 1960, he explicitly rejected the idea of a solid shell in favor of what he called a swarm of objects, each in its own orbit around the Sunday. This remains perhaps the most practical and versatile design for stellar engineering, a configuration that avoids many of the problems inherent in other approaches while providing maximum flexibility. Imagine billions or trillions of independent structures, each following its own elliptical path around the sun, together forming a dense cloud that intercepts a large fraction of the star's radiation. These structures might vary enormously in size, purpose, and design. Some could be vast solar collectors, thin films tens or hundreds of kilometers across, composed of photovoltaic materials or heat engines, designed purely to capture photons and convert them to usable energy. Others might be habitats, rotating cylinders or spheres where billions of people live and work, complete ecosystems enclosed in shells of metal and glass. The orbital mechanics of a Dyson swarm are complex but manageable. At Earth's orbital distance of 1 astronomical unit, objects circle the Sun once per year at about 30 kilometers per second. Closer to the Sun, objects orbit faster, farther. Away, they move more slowly. This means we can place swarm components at various distances, creating a three-dimensional cloud rather than a simple, flat disk. The different orbital periods would cause components to slowly drift relative to each other, sometimes approaching closer, sometimes moving apart. But careful initial placement and occasional station-keeping corrections could prevent collisions. One proposed configuration uses a Klemperer rosette, a specific arrangement where objects occupy vertices of a rotating polygon, all orbiting together as a rigid formation. 6 objects equally spaced around a hexagon at 1 astronomical unit could orbit the Sun while maintaining their geometric relationship, simplifying traffic control and coordination. Multiple rosettes at different scales and orientations could nest within each other, building up a complex but stable architecture. Solar sails provide a way to adjust orbits without expending propellant. These ultra-thin reflective sheets, sometimes just hundreds of atoms thick, use the pressure of sunlight itself to push spacecraft in desired directions. By angling the sail relative to the Sun, objects can spiral inward or outward, change their orbital plane, or make other adjustments. A Dyson swarm could incorporate sail technology into many components, giving them the ability to navigate and maintain safe positions over long periods. The modular nature of a swarm offers tremendous advantages. Construction can proceed incrementally, with each new component adding to the total energy capture and living space without requiring any others to be complete first. If a component fails or is damaged, perhaps by a meteor impact or mechanical breakdown, it affects only that local section, not the entire structure. Repairs, upgrades, and expansions can happen continuously without shutting down the whole system. Diversity becomes possible, with different habitats developing different environments and cultures, different collectors optimized for different frequencies or energy conversion methods. Communication within a Dyson swarm would be a fascinating challenge. Components separated by millions of kilometers couldn't talk via real-time conversation. Even at the speed of light, messages would take seconds or minutes to travel between distant parts of the swarm. Instead, communication would likely be asynchronous, more like email than telephone calls, with sophisticated protocols to handle the delays and coordinate activities across the vast structure. Power distribution poses another interesting problem. Solar collectors might beam energy to other parts of the swarm, using microwave or laser transmission, creating a complex network of power sources and consumers. Or each habitat might be self-sufficient, generating its own energy from local solar collection. The specific architecture would depend on technological capabilities and design philosophy. Centralized versus distributed, networked versus independent. The total mass required for a Dyson swarm depends on how much coverage we want and how efficiently we can build. A sparse swarm intercepting 10% of the sun's light might require the mass of several large asteroids or a small moon, manageable with advanced space industry. A dense swarm capturing 50% or more might require dismantling Mercury or multiple large moons, a vastly larger undertaking. But because construction can proceed incrementally, we could start small and expand over centuries, adding components as resources become available. Temperature control in a swarm is relatively straightforward compared to other designs. Each component radiates its waste heat independently into space. The temperature reached depends on the component's size, albedo, and energy use, but can be adjusted by changing these parameters. Habitats might maintain comfortable temperatures around 280 to 300 Kelvin, while solar collectors operated at higher temperatures to improve energy conversion efficiency. The overall infrared signature would be a complex mixture of different temperatures, potentially making the swarm harder to detect from a distance than a uniform shell. One of the most appealing aspects of a Dyson swarm is its evolutionary nature. It could start as a few experimental structures, growing organically as technology advances and population increases. There's no need for a master plan that must be completed all at once. Early components would provide resources to build later ones, creating a self-sustaining expansion that could adapt to changing needs and capabilities. This makes the swarm the most plausible near-term approach to stellar engineering, something humanity might actually begin in the coming centuries if we continue our expansion into space. The swarm also offers the possibility of disassembly or reconfiguration. If circumstances change, if we want to move to a different star system or radically alter our energy use, we could gradually decommission components, recycle their materials, and rebuild them in new forms or locations. This flexibility means a Dyson swarm isn't necessarily a permanent commitment, but could be an intermediate stage in our civilization's long evolution. Looking up at the night sky from within, a mature Dyson swarm would be a strange experience. The sun itself would be hidden behind layers of structures, visible only as a diffuse glow through gaps in the coverage. The sky would be filled with distant habitats and collectors, some shining brightly with reflected sunlight, others dark against the stars. Navigation would require sophisticated systems to track the constantly shifting positions of billions of objects. Yet this complex, ever-changing environment would be home, the place where most of humanity lived, worked, and thrived. While Freeman Dyson explicitly rejected the notion of a solid shell surrounding a star, the concept has such appeal in science fiction and popular imagination that it's worth examining seriously. What would it take to build a rigid spherical shell at 1 astronomical unit? Why did Dyson dismiss this approach? Are the problems truly insurmountable, or might advanced engineering find solutions? A solid shell, sometimes called a Dyson sphere in the strict sense, would be a rigid structure completely surrounding the Sun at a distance of about 150 million kilometers. The inner surface might be habitable, with artificial gravity provided by rotation or through some other mechanism, supporting potentially trillions of times Earth's current population. The outer surface would radiate waste heat into space, glowing warmly in the infrared, as Dyson predicted. The first major problem with this design is structural support. In space, there's no ground to build on, no foundation to anchor structures. A solid shell would experience gravitational forces from the Sun pulling it inward, but unlike a planet, which is held together by its own self-gravity, the shell has no such binding force. In fact, the shell is unstable. Any slight perturbation that moves it even slightly off-center would create a gravitational imbalance, with the Sun pulling harder on the closer side, causing the shell to drift further until it eventually crashes into the star. This instability problem is fundamental and cannot be solved with passive structural elements. The shell would need active station keeping, thrusters, or other systems constantly monitoring its position and firing to maintain balance. The energy required for this would be substantial, and any failure of the station keeping system would be catastrophic. Some proposals suggest building the shell in sections that orbit independently but maintain their relative positions, effectively a very dense swarm rather than a true solid structure. The material requirements are equally daunting. Even if we could create impossibly thin and strong materials, say diamond nanotubes just micrometers thick, the shell would still require more mass than exists in several planets. Earlier, we calculated that a 1-meter thick shell at 1 astronomical unit would need about 700 Mercury masses. Even reducing this to millimeter thickness, we're talking about hundreds of times Mercury's mass. No known material has the compressive strength to support such a structure against its own weight without collapsing. Larry Niven, in his famous 1970 science fiction novel Ringworld, proposed a partial solution. Don't build a sphere, build a ring. A Niven ring would encircle the star at a fixed distance, rotating fast enough that centrifugal force counterbalances the sun's gravity. This avoids the instability problem and reduces the mass requirement enormously, since we're only building a ring rather than a complete shell. However, it introduces new challenges related to maintaining the rotation, dealing with the enormous tensile stresses, and the fact that the ring provides no coverage of the star's poles, letting much of its energy escape unused. Even if we somehow solved the stability and materials problems, a solid shell would face thermal challenges. The inner surface, directly receiving stellar radiation, would become extremely hot unless actively cooled. The outer surface would need to radiate all the waste heat from whatever civilization lived inside, requiring precise temperature management across the entire vast area. Any local hotspots or cold spots could create stresses that threaten structural integrity. Access to resources would be another issue. Once enclosed within the shell, how would the civilization mine additional materials from asteroids or moons? They would need to build airlocks or openings large enough to admit spacecraft and bulk materials, creating weak points in the structure. The sun itself would no longer be directly visible from inside, potentially complicating navigation and astronomy. Communication with the outside universe would be limited to signals passing through the shell or transmitted from relay stations on the exterior. Despite these formidable problems, some researchers have explored whether super-advanced materials or exotic physics might make solid shells feasible. Carbon nanotubes have tensile strengths, orders of magnitude higher than steel, though even these might not be adequate at Dyson scale. Graphene, a single layer of carbon atoms arranged in a hexagonal lattice, is the thinnest and strongest material we know, yet still falls short of what would be needed. Perhaps materials we haven't discovered yet, held together by forces we don't yet understand, might have the necessary properties. Active support systems represent another possible approach. Instead of passive structural strength, imagine using magnetic fields, streams of particles, or even light pressure to hold the shell in position. The sun's own energy output could power these systems, creating a dynamic equilibrium where the shell is constantly being pushed and pulled into position. This would be fantastically complex to control, but might avoid the limitations of static materials. One intriguing variation is the bubble world, where instead of a rigid shell, we create a thick atmosphere held in place by some form of containment. This atmosphere could be breathable and support conventional habitats floating within it, like continents in an air ocean. The containment might be provided by electromagnetic fields, rotation, or even by engineering the atmosphere to have a density gradient that keeps it bound. This would avoid the need for structural materials spanning astronomical distances while still providing a habitable environment surrounding the star. Another concept is the swarm world, essentially a Dyson swarm that's so dense it appears solid from a distance, but consists of countless independent components. Each component maintains its own orbit and structural integrity, but they're packed closely enough that from certain perspectives, they present a continuous surface. This gets us the advantages of a swarm while approximating the aesthetic and perhaps functional benefits of a shell. The truth is that a true solid spherical shell, as often depicted in science fiction, remains deeply implausible given known physics and material science. The engineering challenges aren't just difficult, they may be fundamentally impossible to overcome. This is why Dyson rejected the concept in his original paper, focusing instead on swarms of independent objects. The solid shell captures our imagination because it represents the ultimate in megastructure engineering, the most complete possible transformation of a solar system. But imagination must be tempered by physics, and the physics strongly suggests we should look to other designs. Yet, even if we never build solid shells, the concept serves a useful purpose. It represents the limiting case, the maximum possible energy capture and living space a stellar engineering project could provide. By understanding why solid shells are problematic, we learn what constraints any Dyson structure must respect, guiding us toward more practical designs that might actually be built. Beyond the classic Dyson swarm and the solid shell, engineers and scientists have proposed numerous alternative configurations for stellar engineering. Each offers different advantages and faces different challenges. Let's explore some of the most interesting variations. The Dyson bubble represents one elegant solution to several problems. Instead of orbiting the star, the components of a bubble would be stationary, held in place by the outward pressure of sunlight itself. This is possible because photons carry momentum, and when they're absorbed or reflected by a surface, they impart a small push. For sufficiently thin and light structures, this radiation pressure can exactly balance the sun's gravitational pull at specific distances. A Dyson bubble could consist of enormous solar sails, each perhaps millions of kilometers across, but only micrometers thick, positioned to intercept sunlight while remaining stationary relative to the sunday. By adjusting the sail angle and reflectivity, each component could find an equilibrium position. The advantage is that no orbital mechanics are required. Components don't need to circle the star, simplifying coordination and allowing more complete coverage. The disadvantage is that these sails would be incredibly delicate, vulnerable to damage from even microscopic meteorites, and would require active control systems to maintain their precise orientations. The Dyson net takes the bubble concept further, proposing a network of extremely thin wires or cables stretched around the star in a geodesic pattern. The net would be light enough that radiation pressure could support it against gravity, and it could serve as a framework for hanging solar collectors, habitats, and other infrastructure. This would provide structural support without requiring the enormous mass of a solid shell, while still creating a fairly complete coverage of the star. Shkadov thrusters represent a different approach entirely, using stellar engineering not to capture all of a star's energy, but to move the star itself. Russian physicist Leonid Shkadov proposed a giant mirror placed on one side of a star, reflecting light back toward the star. The momentum of the reflected photons would create a net thrust, slowly accelerating the star in the opposite direction. Over millions of years, this thrust could move the star significant distances, allowing a civilization to navigate their entire solar system through the galaxy, avoiding hazards or moving toward desirable locations. A Shkadov thruster wouldn't capture the star's full output, but it would provide mobility, potentially very valuable for a civilization thinking on truly long timescales. The engineering would be simpler than a complete Dyson structure, requiring only a large mirror rather than a full sphere. Combined with a partial Dyson swarm for energy capture, it could offer an attractive compromise between energy harvesting and mobility. Stapleton spheres, named after science fiction author Olaf Stapledon, who envisioned them in his 1937 novel Star Maker, consist of multiple concentric shells around a star, each shell capturing the waste heat from the layer inside it and using it for power. This nested design maximizes energy extraction, potentially allowing a civilization to use the star's output multiple times through successive layers. The innermost shell absorbs the star's direct radiation, heats up, and radiates infrared. The next shell out absorbs this infrared, heats up, and radiates at longer wavelengths. The process continues through multiple layers. The challenge with Stapleton spheres is that each successive shell must operate at a lower temperature, eventually reaching temperatures too cold to efficiently extract work. The second law of thermodynamics limits how many layers can be practical, but even 2 or 3 concentric shells could significantly increase the total energy available to a civilization. The mass requirements would be multiplied by the number of shells, making this an approach for truly advanced civilizations with access to multiple planetary masses of construction material. Matryoshka brains, proposed by Robert Bradbury in the 1990 seconds, take the Stapleton concept and optimize it specifically for computation. Each shell would consist of processors running at different temperatures, with the hottest, innermost layer performing the fastest calculations and dumping waste heat to the next layer out. The civilization would be transformed into a vast computational substrate, potentially running trillions of simulated minds or engaging in scientific calculations of incomprehensible complexity. This design assumes that far future civilizations might value computation more than physical space, preferring virtual worlds to material habitats. The stellar engine concept encompasses several designs where the star itself becomes a propulsion system. Besides Shkadov thrusters, other proposals include the Kaplan thruster, which would use powerful electromagnets to extract material from the star's surface, separate hydrogen from heavier elements, and use the hydrogen for fusion propulsion while dumping the heavier elements back into the star. This would allow both energy extraction and thrust generation, steering the star while also powering a civilization. The engineering would be extraordinarily complex, requiring magnetic fields strong enough to manipulate stellar material and fusion reactors operating at scales we can barely imagine. Ring worlds deserve special mention as one of the most famous alternative designs. Larry Niven's 1970 novel popularized the concept of a ring-shaped structure orbiting a star, with a radius of about 1 astronomical unit and a width of perhaps 1,000,000 kilometers. The ring would rotate to provide artificial gravity on its inner surface, creating a habitable ribbon with a surface area millions of times larger than Earth. Mountains, oceans, and entire ecosystems could exist on this surface, with a day-night cycle created by a second ring of shadow squares orbiting between the ring world and its star. The material requirements for a ring world are somewhat less than a full Dyson sphere, since we're only building a thin band rather than a complete shell. However, the tensile strength requirements are enormous. The structure must withstand the stress of rotation at speed sufficient to generate 1 gravity of acceleration at its inner surface. This requires materials with tensile strengths far beyond anything currently known. The ring world would also be unstable in the plane perpendicular to its rotation, tending to drift toward or away from its star unless actively corrected. Banks orbitals, named after science fiction author Ian M. Banks, are smaller versions of ring worlds, typically around 3 million kilometers in diameter and only a few thousand kilometers wide. These rotate to provide gravity, but are small enough that they don't need unobtainable materials to hold together. Multiple orbitals could share a star system, each potentially hosting billions of inhabitants, together forming a partial Dyson structure that captures a significant fraction of stellar output while remaining within the bounds of plausible engineering. Topopolis represents yet another variation, a tube-shaped habitat that might wind around a star in complex knots, providing a linear living space, potentially billions of kilometers long. Rotation of the tube around its axis would provide gravity, and the topology could be adjusted to create interesting environments and climates. Multiple topopoli could share a system, weaving between each other in elaborate patterns. This design offers flexibility and redundancy. If one section fails, it doesn't necessarily compromise the rest. Each of these alternative configurations represents a different philosophy of stellar engineering, optimized for different priorities. Dyson bubbles prioritize energy capture efficiency. Shkadov thrusters prioritize mobility. Matryoshka brains prioritize computation. Ring worlds prioritize habitable surface area. The choice among them would depend on what a civilization values, what technologies they can develop, and what resources are available in their solar system. It's also worth noting that these designs aren't mutually exclusive. A civilization might build a hybrid structure, combining elements from different concepts. They might have a partial Dyson swarm for energy collection, a Shkadov thruster for mobility, a few ring worlds or orbitals for populations that prefer planetary-style living, and computational nodes operating as mini Matryoshka brains. The final architecture might evolve over millennia, adding and removing components as needs change, creating something uniquely suited to that particular civilization's history and requirements. The diversity of proposals also tells us something important about the search for extraterrestrial intelligence. We shouldn't necessarily expect alien megastructures to look exactly like what Dyson originally described. They might take forms we haven't imagined, optimized for values and constraints we don't share. When we search the skies for evidence of stellar engineering, we need to keep an open mind about what signatures might indicate technology at work, recognizing that the universe might contain variations and innovations beyond our current concepts. The question of what to build a Dyson structure from is as important as the question of how to build it. We need materials that are strong, light, abundant, and manufacturable in the space environment. We need manufacturing processes that can operate in vacuum and microgravity, handling enormous quantities of raw materials and producing components of unprecedented size. Let's explore the materials science and manufacturing challenges that stellar engineering would face. Starting with abundances, the most common elements in the solar system, aside from hydrogen and helium, which are mostly in the sun and gas giants, are oxygen, carbon, nitrogen, silicon, magnesium, iron, and sulfur. These are the building blocks we have to work with. Fortunately, they're also the basis for many useful materials. Silicon and oxygen combine to form silicates, the primary constituent of rocky planets and asteroids. Iron and other metals are abundant in metallic asteroids. Carbon can form diamond, graphite, or more complex structures like carbon nanotubes and graphene. Carbon nanotubes deserve special attention as perhaps the most promising structural material for stellar engineering. These are essentially rolled-up sheets of graphene, one atom thick, arranged in cylindrical tubes with diameters measured in nanometers, but lengths potentially unlimited. Carbon nanotubes have extraordinary properties. Tensile strengths more than 100 times that of steel, thermal conductivity better than diamond, electrical conductivity that can be tuned from insulating to metallic, depending on the tube's structure. If we could manufacture carbon nanotubes in bulk and weave them into macroscopic structures, we might create materials light enough and strong enough for Dyson engineering. A cable made of perfectly aligned carbon nanotubes could theoretically support its own weight for hundreds of thousands of kilometers, making it suitable for space elevator tethers or structural elements in orbital habitats. Sheets of nanotube fabric could serve as ultralight solar sails or radiation shields. The challenge is scaling up production from the tiny quantities currently manufactured in laboratories to the millions of tons required for megastructure construction. Graphene itself, single-atom thick sheets of carbon in a hexagonal lattice, offers similar potential. It's the strongest material ever tested relative to its thickness, essentially unbreakable, yet completely flexible. Graphene is also an excellent conductor of heat and electricity, and can be made transparent or opaque, depending on how many layers are stacked. Large sheets of graphene could serve as solar collectors, habitat windows, or thermal radiators. Again, the challenge is manufacturing, growing perfect graphene sheets, larger than laboratory samples, and assembling them into functional structures. For habitat shells and pressure vessels, we might use aluminum or titanium, both relatively abundant and well understood from aerospace applications. These could be manufactured in space from lunar or asteroid material using solar-powered smelters and refineries. Aluminum has the advantage of being lightweight and corrosion-resistant, while titanium offers higher strength-to-weight ratios and better performance at temperature extremes. Composite materials combining metal matrices with carbon fiber or nanotube reinforcement could offer the best properties of both. For solar collectors, we need materials that efficiently convert sunlight to electricity or heat. Silicon photovoltaics are well-established technology, though the energy payback time, how long a panel must operate to generate the energy required to manufacture it, needs to be minimized for Dyson applications. Thin-film solar cells using cadmium telluride or copper indium gallium selenide offer high efficiency with reduced material requirements, but some of these elements are relatively scarce. Organic photovoltaics or quantum dot cells might offer alternatives, though their efficiency and longevity need improvement. Heat engines provide another approach to energy conversion. These could use focused sunlight to heat a working fluid, which drives turbines to generate electricity. Stirling engines or Brayton cycle turbines could operate in space vacuum, and their efficiency improves at higher operating temperatures. Materials that can withstand extreme heat while maintaining structural integrity, such as tungsten, molybdenum, or ceramic composites, would be essential for high-temperature components. Manufacturing in space requires fundamentally different approaches from Earth-based industry. There's no atmospheric oxygen to rust metals or interfere with sensitive processes. There's no gravity to separate liquids from gases or to drive convection. There's no water for cooling or chemical processing. But there are also advantages. Hard vacuum provides ideal conditions for many chemical reactions and material depositions. Solar energy is abundant and constant, and objects can be easily manipulated regardless of their mass, since there's no weight. Self-replicating factories represent the key to manufacturing at Dyson scale. These would be autonomous systems capable of mining asteroids or planetary material, extracting necessary elements, and constructing both Dyson components and copies of the factory itself. The design might include mining robots that break apart asteroids and transport material to processing facilities, refineries that separate elements using electromagnetic or chemical processes, manufacturing systems that shape materials into required forms using 3D, printing, vapor deposition, or other techniques, assembly robots that put together large structures from smaller components, quality control systems that inspect finished products and reject defective items, replication lines that construct new factories from the same materials used for Dyson components. The replication rate determines how quickly the swarm can grow. If each factory takes 1 year to build a copy of itself and then begins building Dyson components, the number of factories doubles annually. Starting with 1 factory, we'd have 2 after 1 year, 4 after 2, 8 after 3, and so on. After 20 years of exponential replication, we'd have over 1 million factories. After 30 years, over 1 billion. This exponential growth is powerful, but must be carefully controlled to avoid consuming all available material in factories rather than useful structures. Programming these factories requires sophisticated artificial intelligence. They must make decisions about where to mine, how to respond to equipment failures, when to build new factories versus Dyson components, and how to coordinate with other factories to avoid conflicts. The AI must be robust enough to handle unexpected situations, but constrained enough that it doesn't evolve in dangerous directions. This is a significant challenge in its own right, requiring advances in machine learning, robotics, and autonomous systems. Quality control becomes critical when building structures at astronomical scales. A single defective component in a Dyson swarm might cause cascading failures if it collides with other components or fails in some critical mode. Manufacturing tolerances must be maintained across millions of factories operating independently in different locations. This might require standardized designs, extensive testing and inspection protocols, and redundancy so that individual component failures don't compromise system functionality. The sourcing of raw materials would likely progress through several stages. Initially, we might use near-Earth asteroids, which are relatively easy to reach but limited in total mass. As capability grows, we'd move to the main asteroid belt between Mars and Jupiter, which contains far more material but requires more energy to access. Eventually, we might begin dismantling planets, starting with Mercury as the closest to the Sun and most convenient for Dyson construction at 1 astronomical unit. The techniques for planetary disassembly are themselves an engineering challenge, requiring massive electromagnetic launchers or other systems to lift material against gravity and place it in orbit. Capturing the sun's energy is only the first step. A Dyson structure must also convert this energy into useful forms and store it for when and where it's needed. The technologies and systems for energy conversion and storage at stellar scales present their own fascinating challenges and possibilities. Photovoltaic conversion, where sunlight directly generates electricity through the photoelectric effect, is the most familiar approach. Modern solar panels on Earth achieve efficiencies around 20 to 25% for commercial products, with laboratory cells reaching over 40% using multi-junction designs that capture different wavelengths with different semiconductor layers. In space, without atmospheric absorption, the available solar spectrum is broader and more intense, potentially allowing even higher efficiencies. For Dyson applications, we'd want to push efficiency as high as possible, since every percentage point gained means more usable energy from the same collecting area. Multi-junction cells using materials like gallium arsenide, germanium, and various 3V semiconductors can capture a wider range of wavelengths. Quantum dot cells or hot carrier cells, still largely experimental, might eventually exceed 50% efficiency by capturing the energy that normally dissipates as heat in conventional cells. The weight per unit of power is equally important. Thin film cells can be made incredibly light, potentially micrometers thick, yielding power to weight ratios measured in kilowatts per kilogram. For solar sails that must be supported by radiation pressure, minimizing mass is crucial. We might engineer films where the solar collection material is just atoms thick, deposited on even thinner supporting structures, creating collectors that are more surface than substance. Thermal conversion provides an alternative to photovoltaics. Here, sunlight heats a working fluid or solid material, and the thermal energy drives turbines or other heat engines to generate electricity. The theoretical efficiency limit for thermal conversion is given by the Carnot cycle, which depends on the temperature difference between the hot and cold reservoirs. The hotter we can make the collector and the colder we can make the radiator, the more efficient the conversion. Some designs propose using focused sunlight to heat materials to thousands of degrees, temperatures where they glow white hot. Ceramic materials or refractory metals can withstand these conditions, and the high temperature enables high Carnot efficiency. The waste heat radiates into space from large radiator panels, potentially covering as much area as the collectors themselves. The advantage of thermal conversion is that it can use well-established turbine technology and isn't limited by semiconductor band gaps like photovoltaics. The disadvantage is complexity and the need for moving parts that might wear out. Thermophotovoltaic cells combine both approaches, using sunlight to heat a material that then emits thermal radiation at specific wavelengths matched to photovoltaic cells. This allows us to engineer the spectrum of light hitting the cells for maximum efficiency. It's particularly useful when dealing with waste heat from other processes, essentially recycling thermal energy that would otherwise be lost. Energy storage at Dyson scales poses interesting challenges. On Earth, we store energy chemically in batteries or mechanically in pumped hydro or flywheels. In space, some of these options are unavailable or impractical. Chemical batteries add mass and have limited cycle lifetimes. Pumped hydro requires gravity and water, but other options emerge. Mechanical flywheels work well in space, especially using high-strength materials like carbon nanotubes. A spinning disk stores energy in rotational kinetic energy, proportional to the square of its angular velocity. In vacuum with magnetic bearings, there's essentially no friction, so a flywheel can store energy indefinitely without loss. Large flywheels could provide gigawatt-hours of storage in relatively compact packages, smoothing out variations in power generation and consumption. Hydrogen-oxygen fuel cells offer high energy density for chemical storage. Water can be electrolyzed using excess solar power during peak generation, splitting it into hydrogen and oxygen gases. These can be stored under pressure or cryogenically, then recombined in fuel cells when power is needed, producing water again in a closed cycle. The technology is well understood from space applications and provides good round-trip efficiency, typically 60 to 70%. Thermal storage might be the simplest approach for some applications. Excess heat can be stored in materials with high thermal mass and released when needed to drive heat engines. Phase-change materials that absorb heat when melting and release it when freezing can store large amounts of thermal energy in compact volumes. For habitats that need both power and heating, thermal storage could serve dual purposes. Superconducting magnetic energy storage, SMES, offers the possibility of storing energy in powerful magnetic fields with almost no loss. Superconducting coils carrying enormous currents create these fields, and in the cold of space, maintaining superconducting temperatures might be easier than on Earth. SMES systems can respond very quickly, absorbing or releasing gigawatts of power in milliseconds, useful for stabilizing power grids or responding to sudden demand spikes. Beamed power transmission would be essential in a mature Dyson structure. Energy collected in one location needs to be transmitted to users potentially millions of kilometers away. Microwave or laser beams can carry power across space with minimal loss, since there's no atmosphere to absorb or scatter the radiation. Large transmitting and receiving antennas or mirrors would form a power grid connecting different parts of the swarm. Microwave power beaming has been demonstrated experimentally on Earth and in space. A transmitter converts electricity to microwaves. A large antenna beams them in a tight beam toward the receiver. And receiving antennas convert the microwaves back to electricity using rectifying antennas, rectennas. The efficiency can exceed 80% for well-aligned systems, and the beams can travel astronomical distances without significant spreading if the antennas are large enough. Laser power beaming offers higher intensity in narrower beams, potentially allowing smaller receiver sizes. Infrared lasers can be generated efficiently using semiconductor diodes, and photovoltaic cells can convert the received light back to electricity. The challenge is maintaining precise pointing over long distances and dealing with the thermal load on both transmitter and receiver. But for applications needing concentrated power delivery, lasers might be preferred. Power management across a Dyson structure would require sophisticated control systems. Supply and demand would vary as different components rotate in and out of direct sunlight, as habitats wake and sleep, as industrial facilities ramp production up or down. An autonomous grid would need to route power from generators with excess capacity to consumers with demand, maintain storage reserves for emergencies, and handle failures gracefully without cascading blackouts. The total power available in a mature Dyson structure would dwarf anything we can currently imagine. Even a sparse swarm intercepting just 10% of the sun's output would provide 3.8 times 10 to the 25 watts, more than 2 trillion times current human civilization's power consumption. This energy could support a population measured in trillions, living at high standards, power interstellar communication and propulsion systems, run computations beyond our comprehension, or engage in engineering projects we can't yet conceive. The bottleneck wouldn't be energy availability, but our ability to use it creatively and wisely. Having explored the physics, engineering, and materials of Dyson structures, let's turn to perhaps the most important question. What would it actually be like to live in such a place? How would human life and society adapt to existence in orbital habitats scattered throughout a solar system, dependent on engineering for every breath of air and sip of water? Habitats in a Dyson swarm would likely take several forms, each suited to different purposes and populations. The most common design proposed is the O'Neill cylinder, named after physicist Gerard K. O'Neill, who developed the concept in the 1970s. These would be rotating cylinders, perhaps 20 kilometers long and 8 kilometers in diameter, with the interior surface serving as living space. Rotation provides artificial gravity through centrifugal force, creating Earth-normal conditions along the cylinder's inner wall. Inside an O'Neill cylinder, you could stand on the curved interior surface and look up to see land, forests, cities, or ocean curving overhead, eventually disappearing into the distance. 3 strips of land might alternate with 3 transparent windows running the length of the cylinder, admitting sunlight reflected in by external mirrors. The day-night cycle could be controlled by adjusting the mirrors, creating whatever schedule the inhabitants preferred. Weather could be engineered, rain scheduled when needed, winds generated by pressure differentials. The ecology of these habitats would be carefully designed closed systems. Plants would photosynthesize, converting carbon dioxide to oxygen and producing food. Animals and decomposers would complete the nutrient cycles. Water would be continuously recycled through natural and engineered processes. Nothing would be wasted. Every atom would have its role in the habitat's metabolism. This would require far more sophisticated ecological engineering than we currently possess, but over centuries we might develop the necessary understanding and control. Smaller habitats could serve specialized purposes. Torus-shaped stations, like Stanford Torrey, might house research facilities or industrial operations. Smaller, non-rotating stations in microgravity could support manufacturing processes that benefit from weightlessness or provide vacation destinations for people wanting to experience freefall. Slow-rotating stations with partial gravity could accommodate people who can't tolerate full Earth gravity or want to experience the freedom of reduced weight. The social organization of a Dyson swarm would likely be decentralized. Each habitat might be politically independent, governing itself according to local preferences. With millions or billions of separate habitats, tremendous diversity would be possible. Some might be traditional democracies, others experimental forms of governance. Some might maintain Earth-like environments and cultures, others might develop entirely new ways of living. This diversity would be a great strength, allowing experimentation and evolution of social forms. Communication between habitats would shape social interactions. Light speed delays mean that conversations with someone on a habitat a few light minutes away would be asynchronous, more like email than real-time chat. This might encourage deeper, more thoughtful communication, but also create distinct social bubbles. Communities defined more by communication latency than by physical proximity. You might feel closer to someone on a habitat with fast data connections than to someone on a neighbouring habitat if those neighbours kept to themselves. Transportation within the swarm would be an interesting challenge. Moving between habitats requires spacecraft capable of matching orbits, which can be energy intensive depending on the distance and orbital differences. Regular transport networks might connect major habitats, like interplanetary bus routes with schedules and waypoints. Personal spacecraft for individuals or small groups could provide flexibility, assuming energy is cheap enough. Travel times could range from hours between nearby habitats to weeks for journeys across the solar system. The economy of a Dyson civilization would be post-scarcity in many respects. With effectively unlimited solar energy and access to asteroid material, the basic physical necessities air, water, food, shelter, power could be provided to everyone at minimal cost. Manufacturing could be largely automated, with self-replicating systems producing whatever goods are needed. In such an economy, what would people do? What would give life meaning when survival is assured and material wealth is trivial? Perhaps attention and creativity become the valuable currencies. People might pursue art, science, exploration, relationships, experiences, things that can't be mass-manufactured. Reputation and respect earned through contributions to culture or knowledge might matter more than ownership of physical objects. Or perhaps we can't predict the values of such a civilization because they would emerge from conditions so different from current human experience that our categories don't apply. Education and personal development would take on new dimensions. With centuries of lifespan possible through advanced medicine and with automated systems handling material needs, individuals could pursue multiple careers or areas of expertise. You might spend a century as an artist, another as a scientist, another as an explorer, continuously learning and growing. The accumulated wisdom of such long-lived individuals could be profound, though societies would need to ensure that the young still had opportunities and that innovation wasn't stifled by entrenched interests. Conflict and cooperation would both persist. Different habitats might disagree about resource allocation, orbital rights, or cultural practices. Without a central government, resolving disputes would require negotiation, arbitration, or perhaps economic pressure, refusing to trade with or provide power to a habitat acting badly. Physical warfare would be catastrophic given the fragility of life support systems, creating strong incentives for peaceful resolution. Mutual dependence for power, for trade, for genetic and cultural diversity would encourage cooperation. The relationship with Earth would be complex. Our birth planet would likely remain culturally and psychologically significant, even as more people lived in space than on the surface. Earth might be preserved as a nature reserve, a memorial to our origins, protected from industrial development. Or it might continue to evolve, home to those who prefer planetary life but no longer the center of human civilization. Visiting Earth could be like visiting a museum or a sacred site, important but not where most people spend their daily lives. Children born in space habitats would be true spacers, knowing planetary life only from stories and visits. They might feel uncomfortable in Earth's gravity, claustrophobic under open sky without visible boundaries. Their identity would be shaped by the habitat they grew up in, by the view of other habitats and stars from their windows, by the knowledge that their world was engineered and maintained by deliberate effort. This might create a different psychology, an awareness of contingency and interdependence that planetary humans lack. Over generations, genetic and cultural drift could create distinct populations adapted to different environments. People living in low-gravity habitats might evolve taller, more slender builds. Those in habitats with high radiation exposure might develop enhanced DNA repair mechanisms. Cultural practices would diverge as habitats developed their own traditions, languages, and social norms. Yet communication and transportation would maintain connections, preventing complete fragmentation while allowing healthy diversity. The view from within a mature Dyson swarm would be unlike anything we've experienced. Instead of a night sky with distant stars, you'd see thousands or millions of habitats, some shining with reflected sunlight, others glowing with the warm infrared of waste heat. Constellations would be artificial, patterns of engineering rather than distant suns. The Earth, if visible at all, would be a small blue dot lost among the myriad structures. You'd live immersed in civilization at astronomical scale, always aware that you exist as part of something vast and collectively created. If Dyson structures exist around distant stars, how would we detect them? What signatures would betray the presence of stellar engineering from thousands of light years away? This question has driven an entire subfield of astronomy, the search for techno-signatures, evidence of technology in astronomical observations. Let's explore how we look for Dyson spheres and what we've found so far. Freeman Dyson's original insight was that the waste heat from a Dyson structure would glow in the infrared, creating a distinctive signature. A star completely enclosed by a Dyson sphere at 1 astronomical unit would be invisible in optical wavelengths, all its visible light absorbed by the structure, but it would shine brightly in the mid and far infrared, around 10 micrometers wavelength. This infrared excess would distinguish it from normal stars. The first systematic searches began in the 1960s, just a few years after Dyson's paper, though instruments at the time were limited. Modern searches have benefited enormously from infrared astronomy satellites, like IRAS, Infrared Astronomical Satellite, Spitzer, WISE Wide Field, Infrared Survey Explorer, and most recently, the James Webb Space Telescope. These instruments have surveyed large portions of the sky in infrared, cataloguing millions of sources and measuring their spectra with increasing precision. The challenge is distinguishing Dyson spheres from natural infrared sources. Many natural objects glow in infrared, young stars still embedded in dusty clouds, older stars shedding material in stellar winds, planetary nebulae, galaxies shrouded in dust from star formation. The key is finding objects that don't fit standard models, that show infrared excess without corresponding visible light in patterns that suggest artificial construction rather than natural processes. One search strategy looks for complete Dyson spheres, objects that should appear as pure infrared sources with no optical counterpart. Astronomers can cross-reference optical catalogues with infrared catalogues, looking for sources that appear in infrared but not in visible light. So far, most such candidates have turned out to be distant galaxies or objects behind obscuring dust, natural explanations for the lack of optical emission. A true complete Dyson sphere remains elusive. Partial Dyson structures, swarms that intercept only a fraction of their star's light, would be easier to detect in some ways because the star would still be visible optically. We'd look for stars with unusual amounts of infrared emission compared to their visible brightness, more than can be explained by stellar atmospheres or circumstellar dust. The infrared excess would need to have the right temperature, consistent with waste heat from technology, rather than natural dust or planets. Several interesting candidates have emerged over the years. Tabby's star, officially designated KIC 8462852, showed unusual dimming patterns observed by NASA's Kepler spacecraft. Between 2011 and 2013, its brightness dropped by up to 22%, far more than could be explained by transiting planets. Various explanations were proposed, including a partial Dyson structure under construction. However, subsequent observations showed that the dimming was wavelength dependent, more pronounced in blue light than red, consistent with obscuration by dust rather than solid structures. The current best explanation involves a dust cloud, possibly from a disintegrated comet, though some aspects remain mysterious. WDS J19461790 plus 400,257.6, awkwardly labelled and informally called the Dyson Sphere candidate, appeared in a 2024 study analysing Gaia and WISE data for millions of stars. This object showed significant infrared excess, but after more detailed analysis appeared consistent with a debris disk around a white dwarf or other natural phenomenon. The search continues, with each candidate teaching us more about both astronomical phenomena and how to refine our search criteria. The temperature of the infrared emission is crucial. A Dyson structure at 1 astronomical unit from a Sun-like star would equilibrate around 300 Kelvin, emitting peak radiation around 10 micrometers. Structures at different distances or around different types of stars would have different temperatures. Hot, luminous stars might have Dyson structures at larger distances, creating cooler signatures. Cool red dwarf stars might have closer Dyson structures, creating warmer signatures. By analysing the spectrum, we can constrain both the temperature and the size of the emitting region. Another approach looks for optical transits, analogous to detecting exoplanets, but at much larger scales. If a Dyson swarm passes between us and its star, it would cause the star to dim. The pattern of dimming could reveal information about the structure. Regular dips might indicate evenly spaced orbital components. Irregular dips might suggest a more chaotic arrangement. The depth of transits would indicate how much of the star's light is being intercepted, potentially allowing us to estimate the swarm's coverage. The challenge with transit searches is that they require precise, continuous monitoring over long periods. Dyson components at 1 astronomical unit take 1 year to orbit, so we need to watch stars for years to see repeating patterns. Space telescopes like Kepler and TESS, transiting exoplanet survey satellite, have observed hundreds of thousands of stars with sufficient precision, though their primary goal was finding planets rather than megastructures. Analysis of their data for anomalous transits continues, with machine learning algorithms helping to identify candidates in the vast dataset. Variability offers another clue. Natural stars can be variable, but usually in predictable ways related to stellar physics, pulsations, rotation, magnetic activity. A Dyson structure under construction might show increasing infrared emission over years or decades as more components are added and coverage grows. Or we might see irregular variations as different parts of the swarm move in and out of our line of sight, creating a light curve that doesn't match any natural stellar model. Spectral features could provide strong evidence. While thermal emission from heated structures would be approximately blackbody, there might be absorption or emission lines from specific materials or processes. For example, if the structure uses photovoltaic conversion with silicon-based cells, there might be spectral signatures of silicon at specific wavelengths. Laser power beaming between components might create narrow emission lines at the laser wavelength. These would be smoking gun evidence of technology, though detecting faint spectral features from thousands of light years away remains at the edge of current capabilities. Radio emission represents another possibility. A technologically advanced civilization might communicate using radio waves, either internally within their Dyson structure or broadcasting to other stars. Programs like SETI, Search for Extraterrestrial Intelligence, have monitored radio frequencies for decades, looking for narrow-band signals that couldn't be produced by natural processes. Combining radio searches with infrared searches could be powerful. A star with both infrared excess and interesting radio emission would be a compelling candidate for further study. The James Webb Space Telescope, launched in 2021, provides new capabilities for Dyson Sphere searches. Its sensitivity in mid-infrared allows detailed spectroscopy of thousands of stars, potentially revealing subtle signatures invisible to earlier instruments. JWST can observe faint objects with unprecedented clarity, possibly detecting partial Dyson structures that earlier surveys missed. As it compiles data over years of operation, analysis might reveal patterns or anomalies worthy of follow-up. Ground-based telescopes continue to contribute. Improved infrared detectors and adaptive optic systems allow high-resolution observations from Earth's surface despite atmospheric interference. All sky surveys are finding infrared sources for more and more detailed catalogues to mine for anomalies. The synergy between ground and space observations, between different wavelengths and different search strategies, creates a comprehensive search, likely to find Dyson structures if they exist in our cosmic neighborhood. The search for Dyson spheres connects to one of the most profound questions in science. Where is everybody? The Fermi paradox, named after physicist Enrico Fermi, who famously asked this question over lunch in 1950, notes the apparent contradiction between high estimates for the probability of extraterrestrial civilizations and the complete lack of evidence for their existence. If intelligent life is common and Dyson structures are a natural stage of development, we should see them everywhere. The fact that we don't demands explanation. Several categories of solutions to the Fermi paradox have been proposed, each with implications for what we should expect in our astronomical searches. Let's explore these and consider what they might mean for stellar engineering and technosignatures. First, perhaps life itself is rare. Maybe the origin of life requires such specific conditions, such unlikely molecular coincidences, that Earth is one of very few places in the galaxy where it emerged. This would explain why we see no evidence of other civilizations. They simply don't exist. However, discoveries of potentially habitable exoplanets, organic molecules in space, and the rapid emergence of life on early Earth all suggest that life might not be as rare as this solution requires. Still, we can't rule it out until we actually detect life elsewhere. Second, perhaps intelligence or technological civilization is rare. Life might be common, but most of it remains microbial, never developing complex multicellularity, nervous systems, or the specific kind of intelligence that builds technology. Earth's own history shows that life existed for billions of years before developing human-level intelligence, and there's no guarantee that intelligence is an inevitable outcome of evolution. Perhaps most planets with life remain in microbial stages indefinitely. The Great Filter hypothesis suggests there's some step in the progression from non-life to galaxy-spanning civilization that's extraordinarily difficult to pass. This filter might be behind us. Perhaps the origin of life or development of complex cells was the hard step, and we've already passed it. Or it might be ahead of us. Perhaps technological civilizations inevitably destroy themselves before reaching stellar engineering capability, through nuclear war, environmental collapse, or some other catastrophe we haven't yet encountered. If the Great Filter is ahead of us, this has ominous implications. Every step toward becoming a spacefaring civilization capable of building Dyson structures might bring us closer to the precipice that destroyed countless civilizations before us. The absence of detectable megastructures would then be evidence that technological societies face some universal threat they cannot overcome. This is perhaps the most unsettling solution to the Fermi paradox, suggesting our silence in the universe might be protective rather than disappointing. Alternatively, perhaps civilizations simply don't build Dyson structures. Maybe there are technical obstacles we haven't foreseen that make stellar engineering impossible or impractical. Or perhaps civilizations consistently choose not to build them, either because they find better alternatives, because they value preservation of natural stellar systems, or because they transcend physical needs entirely. Maybe advanced civilizations migrate into black holes, create pocket universes, upload themselves into virtual realities, or undergo some other transformation that makes them uninterested in stellar-scale engineering. The zoo hypothesis suggests that alien civilizations exist and are aware of us but deliberately avoid contact, perhaps to let us develop naturally like animals in a nature preserve. If true, they might deliberately avoid building obvious megastructures near us, or might use cloaking technology to hide their presence. This seems like special pleading. Why would all civilizations agree to hide? But we can't absolutely rule it out. Timing offers another possible explanation. The universe is about 13.8 billion years old, but the earliest generations of stars contained almost no heavy elements, making planet formation and thus life impossible. It wasn't until stars had lived and died, enriching space with carbon, oxygen, silicon, and metals through supernovae, that rocky planets and complex chemistry became possible. Perhaps we're among the first civilizations to arise, and when we look out at the universe, we're looking at a galaxy still mostly empty, a cosmic ecosystem still in its early stages. This solution has an appeal because it avoids both pessimism about our future and the puzzle of why we seem to be alone. We might be pioneers, the first or among the first technological species to contemplate stellar engineering. Our descendants might be the ones building Dyson Spheres that civilizations millions of years hence will detect. This places enormous responsibility on us. The choices we make now could influence the entire future character of intelligence in the galaxy. Distance and detection limits might also play a role. Even if Dyson structures are common, they might be difficult to detect at interstellar distances. A partial Dyson swarm around a star thousands of light years away would appear as a faint infrared source, hard to distinguish from natural phenomena without careful analysis. If most civilizations build sparse swarms rather than complete spheres, or if they build at distances or temperatures different from what we've primarily searched for, we might simply be missing the signatures even though they're there. The question of motivation is also worth considering. We assume that civilizations will continue to grow, expanding their energy use and eventually building megastructures to meet their needs. But what if growth plateaus? What if mature civilizations become more efficient rather than larger, learning to do more with less energy? What if they achieve a sustainable equilibrium at population and energy use levels far below what Dyson structures would require? Then stellar engineering would be unnecessary, and we wouldn't see it even though advanced civilizations exist. Some researchers have proposed that consciousness or intelligence might not require much energy at all. If civilizations eventually upload into digital substrates running on highly efficient quantum computers, they might support trillions of minds using less power than current human civilization. Why build a Dyson sphere when you can run your entire civilization on the power from a few nuclear reactors? This would make advanced civilizations nearly invisible, their signatures too faint to detect across interstellar distances. The dark forest hypothesis, popularized in science fiction but also discussed seriously by some scientists, suggests that the universe is dangerous and publicizing your existence is deadly. If predatory civilizations roam the galaxy, destroying any competition they detect, then staying hidden is the rational strategy. Dyson spheres, being highly visible, would be advertisements inviting destruction. Civilizations might exist but remain deliberately quiet and undetectable. Whether such predators could actually exist and enforce galaxy-wide silence remains debatable. Each of these solutions has different implications for what we should expect in our searches and how we should conduct ourselves as an emerging technological civilization. If the Great Filter is ahead of us, we should focus on identifying and mitigating existential risks. If we're early, we should emphasize survival and expansion, becoming the civilization that eventually fills the galaxy. If other civilizations are hiding or have transcended physical needs, we need to consider whether our search strategies are even looking in the right places. The absence of detected Dyson structures, while not conclusive proof of anything, does constrain the possibilities. It tells us that complete Dyson spheres around sun-like stars within a few thousand light-years of Earth, if they exist, are rare enough that we haven't found them yet. This either means civilizations are rare, or they don't build complete spheres, or we're not detecting them effectively. Each of these deserves serious consideration as we refine our searches and think about humanity's long-term future. While Dyson spheres represent perhaps the most dramatic form of stellar engineering, they're not the only possible techno-signatures we might detect. Let's explore other evidence of technology that astronomical observations might reveal, some perhaps even more telling than megastructures. Atmospheric biosignatures on exoplanets have received enormous attention as a way to detect life, but technological civilizations might produce atmospheric technosignatures, pollution, or industrial products detectable in planetary spectra. Chlorofluorocarbons, compounds that don't occur naturally, but were produced in vast quantities on Earth for refrigeration and aerosols before being banned due to ozone depletion, would be clear signatures of technology if detected on an exoplanet. Similarly, nitrogen dioxide from combustion or various industrial chemicals might indicate technological activity. The James Webb Space Telescope and future missions like the Large UV Optical Infrared Surveyor could potentially detect these molecules in the atmospheres of nearby rocky exoplanets through transit spectroscopy, analyzing the light from the parent star as it filters through the planet's atmosphere. The challenge is sensitivity. Detecting trace gases in atmospheres light-years away requires extraordinary precision and long observation times. But if a civilization engages in industry at planetary scales, their atmospheric pollution might be detectable. Artificial illumination offers another possibility. Human civilization now produces enough artificial light at night that Earth shines brighter on the night side than on the day side in certain wavelengths. If we can detect the day-night contrast on exoplanets, unusual brightening on the night side might indicate cities and infrastructure. The light would need to be distinguishable from natural phenomena like auroras or volcanism, but spectral analysis might reveal the characteristic signatures of artificial lighting, particularly if the civilization uses specific technologies like sodium vapor lamps or LEDs. Heat signatures from industrial activity might be detectable even without complete Dyson structures. Large-scale manufacturing, power generation, or data centers would produce waste heat, creating localized warm spots on a planet or in a solar system. If we can map the thermal emission from exoplanets and their neighborhoods with sufficient resolution, we might find temperature distributions that don't match natural processes, suggesting technological heat sources. Radio and laser transmissions remain among the most promising techno-signatures. While SETI has listened for deliberate messages, civilizations might also leak radio and television broadcasts, radar, or telecommunications signals into space unintentionally. These would be much weaker than a deliberate beacon, but might still be detectable if we're close enough and listening at the right frequencies. Narrowband radio signals, particularly if they show patterns like modulation or drift in frequency due to planetary rotation, would be compelling evidence of technology. The Square Kilometre Array, a next-generation radio telescope under construction, will have unprecedented sensitivity for detecting faint radio signals from exoplanets. It might pick up the radio equivalent of Earth's television broadcasts from nearby star systems, or detect the much stronger emissions from an advanced civilization's power transmission or deep space communications. The challenge is distinguishing artificial signals from the many natural radio sources in space, a problem requiring sophisticated signal processing and pattern recognition. Laser pulses represent another communication channel. A powerful laser, directed at Earth, even briefly, might be detectable by optical SETI programs that watch for bright flashes in visible light. These programs observe thousands of stars, looking for brief intensity spikes that could be artificial pulses. A nanosecond laser pulse from an advanced civilization could temporarily outshine their entire parent star in that brief moment, making it detectable across thousands of light years. No confirmed detections have been made yet, but the search continues. Stellar engineering beyond Dyson structures might be detectable. If civilizations can move stars, perhaps using Shkadov thrusters or other stellar propulsion systems, we might notice stars moving in unusual ways that don't match standard stellar motion models. A star accelerating in a specific direction, particularly if multiple stars show similar anomalous motion suggesting deliberate coordination, would be interesting. This requires extremely precise astrometry, mapping stellar positions and velocities with high accuracy, something missions like Gaia are providing. Artificial structures in space, even if not complete Dyson spheres, might be visible. Very large space stations, orbital rings around planets, space elevators, or arrays of solar collectors could potentially be detected through high-resolution imaging or through the occultations they cause. The James Webb Space Telescope can resolve features on some nearby exoplanets. Future telescopes with even larger mirrors or using interferometry might detect artificial structures orbiting those planets. Relativistic travel signatures might reveal technological civilizations exploring or colonizing the galaxy. A spacecraft traveling at a significant fraction of light speed would produce various detectable effects. Relativistic beaming of any radiation it emits, interactions with the interstellar medium creating a bow shock, and possibly visible exhaust if it uses fusion or antimatter propulsion. Surveys looking for unusual transient phenomena might stumble across such signatures. Nuclear signatures could betray technological activity. If civilizations use fission or fusion power on large scales, they might produce characteristic isotope ratios or gamma-ray emissions detectable across interstellar distances. A supernova-like burst that doesn't quite match natural supernovae might be a catastrophic accident with nuclear weapons or reactors. While we hope civilizations avoid such disasters, they would certainly be detectable if they occurred. Mining operations on asteroids or planets might be visible through changes in albedo or composition of those bodies. If a civilization systematically dismantles asteroids for construction material, the asteroid belt might become depleted or show unusual size distributions. If they mine planets, particularly Mercury, which is closest to the Sun and most convenient for Dyson construction, we might see changes in that planet's brightness or spectrum as material is removed. This requires observations over many years to detect changes, but long-term monitoring programs could potentially reveal such activity. Waste products from industrial processes might create detectable clouds or rings around stars. If a civilization extensively processes asteroidal or planetary material, they might produce dust, gases, or debris that doesn't match natural circumstellar material in composition or distribution. Unusual spectral features in debris disks around stars might indicate technological processing rather than natural planetary formation or collision processes. The diversity of possible technosignatures suggests we should cast a wide net in our searches. Rather than focusing exclusively on any single signature like Dyson spheres or radio signals, comprehensive surveys across multiple wavelengths and phenomena might be most effective. This is the approach modern technosignature studies are taking, looking for any anomalies that don't fit natural models, any patterns that suggest intelligence rather than physics. It's also worth noting that we might detect technosignatures we haven't yet thought of, phenomena that we'll recognize as artificial only after we observe them and puzzle over their nature. The history of astronomy is full of discoveries of unexpected phenomena, pulsars, quasars, gamma-ray bursts, that initially seemed mysterious but turned out to be natural. Perhaps future surveys will find something equally unexpected that turns out to be technological. Keeping an open mind and carefully investigating anomalies, rather than immediately assuming natural explanations, might be key to finally answering whether we're alone. As we come to the end of our journey through the physics, engineering, and search for Dyson spheres, let's return to the question that underlies everything. What does this mean for humanity? Should we build a Dyson sphere? Could we? And if we did, what would we become? The decision to undertake stellar engineering would be perhaps the most consequential choice our species has ever made. It would commit us to a path that transforms not just our technology, but our fundamental relationship with nature, with each other, and with the cosmos itself. Let's consider what would be required and what we might gain or lose. First, we would need to survive the near-term challenges that currently threaten our existence. Climate change, nuclear weapons, pandemics, artificial intelligence risks. These are the great filters we face now. Building a Dyson sphere requires thinking in terms of centuries and millennia, but we must first ensure we have centuries and millennia ahead of us. This means solving coordination problems, learning to act collectively for long-term benefit, developing wisdom to match our power. Assuming we survive and continue to develop, the path to stellar engineering would likely follow the trajectory we discussed. Lunar bases, establishing space industry, asteroid mining providing raw materials, orbital habitats hosting growing populations in space, self-replicating machines enabling exponential expansion. Each step would be significant in itself, improving human capabilities and understanding, before eventually culminating in structures at stellar scales. The motivations for building a Dyson structure would likely be practical rather than ideological. As human population grows, as we exhaust easily accessible resources on Earth, as we face the reality that planetary living space is finite, expansion into space becomes not a choice, but a necessity. A Dyson swarm would be the mature endpoint of this expansion, the point at which we've utilized the majority of available resources and energy in our solar system to support our civilization. But we should also ask whether unlimited growth is desirable or inevitable. Perhaps humanity reaches an equilibrium population and energy use, stabilizing at levels that don't require stellar engineering. Perhaps we develop technologies that make us more efficient rather than simply larger. Perhaps we decide that preserving natural space and limiting our footprint is more important than maximum expansion. The choice is ours to make, collectively, over the coming centuries. If we do build Dyson structures, the transformation of human civilization would be profound. We would become a true spacefaring species, with the majority of humanity living not on planets but in constructed habitats. Our identity would shift from planetary creatures to cosmic architects, beings who shape their environment at astronomical scales. The cultural, psychological, and philosophical implications of this shift are difficult to predict but certainly immense. The diversity of possible habitats means humanity might fragment into distinct populations, each adapted to their environment and culture. Some might cling to traditional human forms and experiences, maintaining Earth-like habitats. Others might enhance themselves through genetic engineering or merging with technology, becoming post-human in various ways. Still, others might upload into purely digital existence. A mature Dyson civilization would likely encompass tremendous variety, unity through shared infrastructure, but diversity in individual choices. The question of other civilizations looms over these considerations. If we build a Dyson sphere, we make ourselves visible to anyone watching from afar. Our infrared signature would announce our presence across thousands of light years. Is this safe? Are there dangers in the darkness between stars? Or is silence itself the danger, isolation preventing us from joining a cosmic community of minds? We don't know, and we won't know until we either detect others or make ourselves detectable and see what happens. Our responsibility to potential life elsewhere in the universe is worth contemplating. If we're early, if we're among the first technological civilizations, then our choices might set precedents or establish patterns that influence galactic civilization for billions of years. How we treat other species, how we manage our expansion, whether we build sustainably or exploit ruthlessly, these choices might matter at cosmic scales, shaping the future character of intelligence throughout the galaxy. The search for existing Dyson spheres should continue and intensify. Every star we examine, every infrared survey we conduct, every anomaly we investigate brings us closer to answering whether we're alone. The discovery of even one confirmed Dyson structure would revolutionize our understanding of our place in the universe. It would prove that stellar engineering is possible, that civilizations can survive long enough to build such structures, that we're not alone in contemplating these vast projects. If we never find evidence of other civilizations, this too tells us something important. It suggests either that technological life is rare, that we're among the first, or that there's something about stellar engineering we don't understand that makes it less universal than we assume. Each possibility has profound implications for how we should proceed. The timeline for humanity potentially building Dyson structures stretches across centuries or millennia. No one alive today will see the completion of such a project, even if we started immediately. This requires a kind of patience and long-term thinking that's foreign to modern culture. We must plant seeds that will grow into forests we'll never walk in, invest in, futures we'll never personally experience. This is simultaneously humbling and ennobling, connecting us to the deep time of cosmic history. There's also beauty in the vision of Dyson structures, something that speaks to our aesthetic and spiritual sensibilities beyond practical concerns. The image of a star wrapped in a gossamer sphere of habitats and collectors, glowing warmly in infrared, humanity spread across billions of homes under artificial skies. There's poetry in this. It represents hope, the belief that we can overcome our current limitations and build something magnificent, that our story continues far beyond these early, troubled chapters. As you drift toward sleep tonight, imagine looking back at our solar system from a great distance, thousands of years in the future. The sun still shines, but now it's surrounded by a complex network of structures, a Dyson swarm catching its light and transforming it into life, thought, and art. Trillions of humans, and perhaps other intelligences we've created or encountered, live in this vast constructed realm, pursuing purposes we can barely conceive. They remember Earth, our blue origin world, preserved and honored. They remember this moment, when we first imagined what they became. That future isn't certain. It requires choices, sacrifices, wisdom, and luck. But it's possible, permitted by the laws of physics, achievable through patient engineering. Whether we pursue it depends on us, on whether we survive our current challenges and maintain the vision of something greater than ourselves, something worth building, even knowing we'll never see its completion. The stars await, ancient and patient, their energy streaming into the void. Perhaps we'll learn to catch that light, to wrap our parent star in structures of purpose and beauty. Perhaps we'll join or establish a community of stellar engineers, civilizations spanning solar systems and communicating across the light years. Or perhaps we'll choose different paths, finding meaning and fulfillment in ways that don't require such vast engineering. Whatever we choose, the fact that we can imagine Dyson spheres, that we can calculate their physics and plan their construction, that we can search for them around distant stars, this itself is remarkable. We've come so far from our ancestors who gazed up at the night sky in wonder, not knowing what the stars were. We've learned that the universe operates according to comprehensible laws, that energy and matter can be shaped by intelligence, that the future is not predetermined but open to our choices. So dream of Dyson spheres, of humanity spread across the cosmos, of energy captured and transformed into consciousness, experiencing and understanding the universe. Let these visions inspire and guide us, reminding us of what we might become if we survive and choose wisely. The path is long, the challenge is immense, but the destination, a future among the stars, building structures that wrap suns, remains possible, waiting for us to reach toward it. Thank you for joining me on this exploration of stellar engineering. May your dreams be filled with cosmic visions, and may we all contribute, in our small ways, to the long journey toward the stars. Until next time, this is Whispering Universes, where we contemplate the grandest possibilities of our cosmic future. Sleep well and dream of stars wrapped in light.